Usually I talk about IPv6, and that's why I started saying a new internet. But today I am not talking about IPv6, so it's a kind of trick. This is a quick introduction to HTTP2, QUIC, DOH, and also DOT. The idea is not to be a very in-depth technical presentation. There are some technical details. Feel free afterwards or later on today or tomorrow to ask me questions if we don't have the time today. Okay, I'm trying to see my slides from here, but it's difficult. Let's see if I can move this like that. No, that way. I cannot see. I am short, so I cannot see my slides. That's okay. Now I am ready. Okay. So, internet is changing. Since several years ago, more and more traffic is going through HTTP and HTTPS, so it's port 80 and port 443. And up to now, only DNS was not using those ports, okay? This change is due to different factors, including people willing to be able to easily filter the traffic, okay? So as much as you can filter just a couple of ports, much easier is your work, right? This means that applications are obligated to use those ports if they want to avoid being filtered, right? The advantage is that just by improving those protocols, those ports, you do a lot instead of changing more things. So everything is in one side good and in the other side good as well for the people that is developing the protocol, right? There is also more perception of that security and privacy are key for everyone. I think that's clear. So we can take the opportunity moving the traffic through a specific ports to make that in an easier way. That's part of the thing. So a bit of history. Some of you already know this. Originally, HTTP was defined in 91 and then improved in 99 with HTTP 1.1. Websites have greatly evolved since then, and we have changed the way that the websites work from a very few kilobytes to few megabytes and hundreds of objects in a single web page. What happens is that HTTP 1.1 was not designed for that and does not perform very well on that situation. According to this, Google started some kind of experiment in 2009, and they call it this SPDY. The idea of SPDY was doing multiplexing. So concurrent requests over a single TCP connection are done. Compression and reduction of the headers, the HTTP headers, some kind of prioritization of the assets, and then a function that they call it server push. So some of the objects can be pushed into the browser, into the client, even before the client is already requesting them. SPDY is a tunnel of HTTP on top of HTTPS. It requires that both sides, the server and the browser, the client, support it. And in 2016, even being just an experiment, not an official protocol, it was already working in 90% worldwide traffic. Okay, so because Google is Google, they succeed to penetrate with this kind of experiment very quickly in a lot of the traffic. SPDY is using what they call the next protocol generation, NPN, to negotiate the SPDY with the TLS server. This is important because this is one of the changes that we did when moving to HTTP2. So the move from SPDY to HTTP2 has been started in 2012 by the IETF working group HTTP-based as the starting point of HTTP2. SPDY was considered. Okay, so basically we can say today that most of the work done by the project, the SPDY project by Google, is what we have today as HTTP2, and it has been approved as a standard in 2015. Is not requiring anymore the support of HTTPS. However, most of the vendors for browsers are implementing it only with TLS. So it means, in fact, in practice, is HTTPS basically. This is not a big problem today anymore, because since a few years ago we have the facility to run things like Let's Encrypt that allow to have free certificate to everyone. So it's not really that a trouble. Which TLS, it's using now, instead of NPN that I just mentioned in the previous slide, is using ALPN, which is Application Layer Protocol Negotiation. That's the big change between SPDY and HTTP2. It's true that the earlier implementations were supporting as well NPN because the SPDY support, but well, the main difference is in the case of NPN, the client is making the choice of what protocol support, while in ALPN, the client gives the server a list of the different protocols, so the server picks one. Okay, that's the main difference between both implementations, let's say. There is a global support for HTTP2. I put there a link to a web page that is updated with all the implementations. So if you look at it, you will see that it's really global support. Websites using it, this is websites, not traffic, is 41% worldwide. But if you look at the top websites, even the big content providers, all of them support it. So in terms of traffic, it's much higher, but I was not able to find more specific data about that. I updated this slide yesterday night. So this is 41% is the last figure that it was beginning of August. Okay, so it's quite recent data. In the web pages that I am citing there, you will find also forecasting of how they predict that it's going to grow the support and so on. Now, just a few pictures. Most of them I did not them, so I put the reference to the original websites. Those websites contain also additional technical information if you want to complement this knowledge. So the difference between HTTP 1.1 versus HTTP 2 with the multiplexing, and the inside multiplexing, how it works in a conversation between a server and a client, right? It's basically the concept that we all have for multiplexing, nothing new here in theory. Now, if we go into the technical details very quickly, I am not sure how I am doing with the time. Let me check. Yeah, okay. I am more or less okay. We have protocol, which is easier framing, different frame types. There are 10 different frame types right now, 2 to map HTTP.1.1, and then features for data and headers, okay? Then we have the multiplexed streams that I already mentioned in the previous slide, priorities and dependencies, the header compression, call it HPAC, and waste bandwidth, the server push that was already available in SPDY, and the flow control. That's the basic aspects if you go to read this RFC 7540. Okay, so summary view of HTTP2 will be one TCP connection. You have the request, the streams are multiplexed, then are priorized. You have the binary framing and the compression, which is the HPAC. That's basically, in short, in a diagram, what you have with HTTP2. There are also extensions. I am not going to go into this slide, but you can check it later. And well, it's a future grow path for extending HTTP2, right? Implementing HTTP2, if you are running Apache, which this slide, just with this slide, you are able to update your Apache server to run HTTP2. Okay, so here you have step by step how you actually do that. It's really, really, really simple. I have been using this for, I don't know, 3 or 4 years, even when it was experimental, and I am running about 100 websites on that, and no problem, everything is working fine, even if it was experimental. I took the risk to go ahead. There is here something that I didn't try it myself because I am not running NGN IX, but people confirmed me that it's working. So again, implementing that in another type of server is also really, really easy. I am using Ubuntu, but typically doing in a different Linux implementation will be very, very similar. I'm not sure if you can click the link, the first link, not the second one. This shows in a very, very simple way what is the difference between the speed in between HTTP 1.1 and HTTP 2. Okay, when you click the link, we tested it before and it worked, so hopefully we don't have demo effect here. Oh, you need to bring the browser and then click. Okay. That's why I prefer using my own laptop, you know? Oh, here is not working. It's coming up. There is a way there to click, I think it's the green button to reload it. Sorry, cannot, okay, skip it. Let's go to the presentation. Please try it yourself later on. It's very, very easy and really, really shows that especially the first time you load the page, it's like 10 times faster, not just 2.5 times faster, but 10 times. Okay, so let's go to the slides and skip that one. Okay, interesting, if you use Chrome, there is an extension that is called HTTP2 and SPDY indicator. I really, really recommend that because you will discover that there are many more websites using HTTP than what you think. And there is also an equivalent to that for, this is not working now. No, it's frozen. Okay, let's try. Yeah, there is an equivalent add-on for Firefox, okay? So I really, really recommend those because you see the arrow to change the color, to display what protocol is using, and if you just put the mouse over there, you see the information on all that, okay? So quite interesting. QUIC, so we changed protocol. During the speedy development, it was obvious also that TCP is not as efficient as it could be if we use instead UDP. So they developed as well what they call it QUIC, which stands for Quick UDP Internet Connections. So in 2016, it was established also a new working group in IETF, the QUIC working group, that is developing. This is not yet a standard, even there is a lot of deployment, experimental, but in production websites, like for example, all the websites from Google, Facebook are deploying this. if you use the applet that I just mentioned for Chrome or Firefox, you will see that also indicates if it's running on QUIC. And what this is basically doing is using a stream multiplexing encrypted transport protocol over UDP, okay? Already deployed by Google. I should mention also Facebook here, but I don't have numbers of the deployment in Facebook, but Google, just Google is 12% of the internet traffic and is 3.3% of the websites of the world. Again, one thing is traffic, another thing is sites, websites. But again, all the websites from Google, Facebook, and a few of the bigger content providers already have it. QUIC standards requires encryption, is using TLS 1.3 and is used to establish the session keys and encrypt all, including the acts. That makes it very interesting because it has some complexity, for example, for passive measurement. So there was a parallel, let's say, draft, internet draft, for what they call it initially a flip bit. And the flip bit was trying to allow passive measurement outside of QUIC, okay? Finally, in the last, I think, 5 versions, they decided to incorporate that. So in version 14 was not there. Right now we are in QUIC version 22, and I think about version 16 or 17 was incorporated in the same document. So the working group decided, well, this is quite interesting, we need that. So even if it's an optional thing, it's not mandatory. I mean, you can implement QUIC and decide if you implement or not the flip bit. If you implement it, of course, you need to do it according to the document. That's the difference. So comparing HTTP versus HTTPS versus QUIC, this is what we have. And the most interesting thing is that allows zero RTT connection establishment. So it gets really, really very interesting. Again, I got this picture from some website. I don't like to make pictures if they are already available, why not? And I just put the reference to where I got the pictures because there are other pictures that may be also interesting to review. Again, QUIC in short. QUIC in short is basically saying that it's transport over UDP, typically implemented as an application process, not kernel. The functionality is equivalent to TCP plus TLS plus the streams, includes the support for the TLS 1.3 and enables zero return trip time. If we compare the protocol stacks, that's what we will get when we have in one column HTTP2, HTTP, the regular one, with SPDY, HTTP with SPDY versus others, including QUIC. Okay, so that's the comparison between all the choices that we have right now. And again, if we compare just HTTP2 versus QUIC, that's what we get. In HTTP2, we can have TLS. In QUIC, TLS is already part of it, okay? TLS 1.3. Implementing QUIC in servers. I did not that yet myself. I plan to do that, but I need to have some free time, and it's not really, really available for me, the free time. So there are here some instructions to do that. Again, I didn't check that myself, but I trust that from other people, they told me, yes, it is working and it's possible. And we have interops in IETF to verify all this. So really, this is reported from people that is working on that. DOH, the IETF DNS over HTTPS, which is what it means DOH, has standardized the encoding of DNS queries and responses over HTTPS, and basically enables DNS to work over paths where existing methods have issues. Transport is suitable for traditional DNS clients. native web applications that use DNS, etc., etc. It's not just a tunnel over HTTP. That's the key thing. Don't confuse that as a tunnel. It's their own protocol to use over HTTPS, right? Interesting, avoids authorities that impose traffic discrimination or censorship to verify what is going there, and that means it's avoiding that discrimination of traffic, right? So it's interesting from that perspective. It's not fun for those governments, but for citizens, it's a different thing. Again, reference to implementations. I have not tested again myself. I plan to, but I trust that people told me this is all working. And well, there are a lot of articles about the implementations by different vendors and browsers of DOH. So yeah, we know that it's really working. DNS over QUIC, and this is the last protocol. Again, I talked about a lot of them. Just a quick introduction. QUIC, not for QUIC the protocol, but QUIC for fast introduction. This is transport of. Oops, what happened? I ran out of time already. Maybe. I think I had 2 minutes. I have my clock here to check. Okay, so as said, with this, what we do is we use QUIC to transport over UDP, and then we do the DNS over QUIC. You have this small picture that shows you that it's just a way to use the QUIC implementation to transport DNS. This is, again, a draft. It's not a standard yet, okay? But I really think it will progress to standard. We'll see. There is a lot of people working on this, so I really think it will go through. Comparison between the different DNS transports. Again, the last column, you see that if we use DNS over QUIC, we have a lot of advantages and we have 0 RTT. Okay, so it gets really, really interesting. I think this graphic is clear, right? It's the only one that has everything green and 0 return time. So why not? So HTTP to reduce the number of round trips, avoids blocking by means of parallel streams. It has a lot of advantages, and de facto, even if it's not the standard, it requires HTTPS, but that's not a problem if you can use free certification entities like Let's Encrypt, for example. QUIC, when it completes the standardization, I don't think it will take more than a few months. I think nothing in the working group is shaking about going against any part of the last version of the document. Will decrease latency, avoid packet loss blocking, and it has a lot of advantages, and even it provides some degree of mobility between different connections, okay? So it has some additional advantages. I know it doesn't like very much the cellular operators, but that's a different history. That's for a specific talk probably. DOH can avoid DNS failures and some censorship. And again, we have DNS over QUIC, which also provides the DNS transfer privacy. Now, the open question, and I am not going to answer that question, is how all this will impact the next year's web traffic and change internet. I really think something is going to happen, especially with QUIC for the cellular operators. But I am not ready now to answer how the battle will finish, or if instead it will be a war. You don't know. Thank you very much. Questions, if any? If not, I am happy after the session or tomorrow. Thank you very much.
Right, thank you, Jordi. Great, so next speaker, as he walks in right on time as well, is Mr. Randy Bush, or AKA the tourist as he calls himself.